talk to you a little bit about the potential role of the lipid metabolism in breast cancer risk and prevention. And so as an epidemiologist, a lot of our work starts with observing what happens in the population. And so I'll just start with showing you some of the recommendations from the World Cancer Research Fund, which is a charity that looks into cancer prevention through changes in lifestyle and diet. And basically what they estimate is that about 6% of all cancers could be due to obesity, which is actually quite a lot if you think about the absolute numbers, because it's more than 17,000 excess cancer cases. And so potentially there is something we can do to prevent that. And so a lot of the work that we've been doing started with a large Swedish observational data set, which is called the apolipoprotein mortality risk study, AMORIS. And so back in the 80s in Sweden, it was very common for employers to pay their employees to have general health checkups every year. And at that time in Stockholm, or the Stockholm area, there was one specific lab that would do all the blood analysis for these annual health checkups. But then in the 90s, it actually became cheaper to have these blood checkups done in hospitals, so the lab actually went bankrupt. But those two brothers who ran the lab then thought, well, we have collected all this information on over 800,000 men and women. We have up to over 500 different markers that we assess in the blood. And in Sweden, because everybody has a unique personal identification number, you can actually then link the lab data to the national cancer data as well as cause of death data and a lot of other registers. And so that's how AMORIS started. And this is just an overview, and I realized sitting in the back before that it may be a little bit hard to read, but it's just to show that apart from the cancer registry and the cause of death registry, you also have inpatient data. So for every time that a person stays in hospital at least one night, you have up to 20 different reasons why the person was in the hospital. We have data on socioeconomic status, we have data on siblings, and there's also the prescribed drug register. And so we started off with looking at about 230,000 women for whom we had measurements of triglycerides, total cholesterol, and glucose. And then from the date that they had their measurement taken, we would follow them up to see whether they had an increased risk of breast cancer when their lipid levels were of an abnormal level. And we actually didn't find very much. The only thing that we found was a very weak inverse association between levels of triglycerides and risk of breast cancer. So what you can see is that if you think that those who have less than 0.7, so the lower level, we see that as a reference, then those who have higher levels, especially as of 0.9, there is a slightly protective effect of the risk of getting breast cancer. So for instance, those who have between 0.9 and 1.3 have a 7% less risk of getting breast cancer compared to those in the lowest quartile. However, we thought this was a fairly weak association because it's actually published as a null finding in the Journal of Cancer Epidemiology, Biomarkers and Prevention. But what we wanted to do is actually look into that in more detail, because at the time when we did the analysis, we didn't have detailed information on the clinical characteristics of breast cancer, because perhaps because we already know that obesity, for instance, is much more strongly associated with postmenopausal breast cancer, so perhaps abnormal levels of the lipid metabolism may also only be associated with certain subtypes of breast cancer. So what we then did is we looked into those women who were diagnosed with breast cancer for whom we also had detailed information of their tumor characteristics. And then we looked at how these different markers of the lipid, but also the glucose metabolism, were associated with different characteristics of breast cancer. And what we found is that if you have high glucose levels, then you are more likely to have a more severe form of breast cancer. And it was the same for the ratio of apolipoprotein B over A1. So if that one was higher, then you also had a higher chance of having a more severe breast cancer. However, you know, as you can see from the odds ratios here, so they're 1.25 and 1.31. So yes, it shows a 25% increased risk or a 31% increased risk. These are still fairly modest odds ratios, and so it just suggests that, there's other factors that really are driving the link between obesity and breast cancer aggressiveness, but it does show that something is going on, which is relevant also given a lot of the research currently on metabolic syndrome, which is a combination of obesity, hypertension, high glucose levels, high triglyceride levels, and low HDL cholesterol levels. So if you have 3 out of 5 of these, you have metabolic syndrome, and that's also been shown to be associated with a higher risk of getting breast cancer. So then another thing we've done is we've looked into statins. So statins being a drug to lower cholesterol levels, because there are some observational studies out there that suggest that when you are on statins, you have a lower risk of getting certain cancers, or if you have cancer and then you're given statins, your cancer is less aggressive. Now, from a biological point of view, there are several hypotheses out there, and some of them are listed here. So cholesterol being a fundamental part of cell proliferation, and then it may have an effect through, so statins then may have an effect through lowering these cholesterol levels, but statins also have an effect on levels of triglycerides. It may be some kind of intracellular pathway. It may be the immune system, because obesity starts to be a low-grade state of chronic inflammation. So there is many different hypotheses out there why statins may potentially have an impact on cancer. Now, if you look at all the observational studies out there, the results are actually quite inconsistent, and there's not many trial data available. So here, we've just checked the literature and looked for the studies, the observational studies that investigated the association between statins and breast cancer. And so the yellow ones did not find an association. The green ones then found that there is actually a reduced risk of breast cancer, and then actually there is one study that found an increased risk of breast cancer. So you can see that there is quite some inconsistency, and it's not just for breast cancer, because we've also done this for prostate cancer, and it's very inconsistent what you find in the literature. So that kind of calls for, well, often then people say, well, if you want to really figure out the effect of a drug on a clinical outcome, you want to do a randomized clinical trial. However, there is not that many studies out there, and so as an epidemiologist, what we then could do is there are advanced epidemiological methods out there which are called causal inference, and what you're going to do then is you're going to use the data from observational studies, and you're going to analyze them as if they were from a randomized clinical trial. So we try to apply those methods to see what we would then find for an association between statins and the risk of breast cancer. And we did it both for breast and prostate cancer. So as I already said, so we're going to treat the observational data as if it were from a randomized controlled trial. And so basically what you're going to do is you're going to come up with a probability for every person in your data set that tells you how likely a person is to get the drug or to not get the drug. So you're going to come up with a probability to say whether you're going to be in the treatment arm or in the placebo arm if it were a randomized trial. And the way you calculate those probabilities is to look into all the potential confounders. So you're going to look into their age, their tumor characteristics, their comorbidities, to figure out what their probability is to get the treatment or the placebo. And so as you can see, we've published this as well, because we did it on prostate cancer. This is published in a urological journal, but we've done exactly the same analysis for breast cancer, and the findings were consistent for the two tumor types. So what we did is then we used data, again from Sweden, from the Uppsala region, and we used the data on breast cancer specific death for women with breast cancer, and then we had matched controls of women without breast cancer. This is just to show you that they're fairly comparable. Well, they're not exactly fairly comparable, because obviously a case will be older than a control, because that's just the nature that you're older when you get your breast cancer. But all this information, because you can see that it's different, so all of this type of information is then taken into account when we calculate the probability of getting the treatment, yes or no. And basically what we found is when we ran this more complicated analysis, so in our preliminary model, we actually found a hazard ratio of 0.56, which we could be quite excited about, because that would mean that actually if you are given statins, you have a 44% less risk of getting breast cancer. However, that would be the model, that is similar to the model that everybody would run in their normal observational analysis. And if we then try to correct for that and use our probabilities of whether you would be given the treatment, yes or no, as if it were a clinical trial, first of all, the hazard ratio goes up to 0.87, so it becomes closer to 1. And you can also see that the confidence interval gets wider. It almost includes 1. And the problem here is that actually if we look at the weights that we estimate, so the probabilities, there is a huge variation. So the weights come from our probabilities, and it's just way too big, which means that we can't run the model. And the problem there is that from a statistical point of view, it's the positivity assumption, which is actually fairly easy to understand from a clinical point of view, because when you do a randomized trial in practice, it means that you're going to randomize people between statins and placebo, so everybody has an equal chance of getting to be in either arm of the trial. But the problem is that if you use observational data for that, potentially everybody has to have the chance to be in the treatment arm or the placebo arm. But you can imagine just in the normal population that if your cholesterol levels are not too high, you're just not going to be given statins. So there becomes problematic, because that's a positivity assumption. Positivity assumption means that everybody has an equal chance of being given statins or not. But in practice, we're never going to give statins to someone who has normal cholesterol levels. And so that brought us then to our conclusion that it's also it's wrong to use the typical methods that are out there, because you can't take everything into account. But you can also not use the advanced methods, because there is a problem that not everybody in real life will be given statins. And so ideally what one would need is we need a better randomized trial or a better observational study where we not only look at whether you're on statins or not, but we also need information on the cholesterol levels. And at the moment, there is no studies out there that have both information on statins and cholesterol levels. So we therefore conclude that we can't really make a statement yet about whether statins are protective for cancer or not, because actually there is no good observational study or trial out there that has all the information available. Obviously, there is a lot of experimental evidence showing a potential effect of statins, but actually from a population point of view, we're still lacking evidence. And so finally, I would like to thank Jennifer Melvin, because she has done most of the work that I've presented here. She was one of our PhD students, and obviously also my collaborators from Sweden, and you for taking time to listen. Thank you very much.
Good, thank you. You finished before your time, in fact, slightly. Yeah, yeah. And now